The goal of this video is to give you some of the highlights, at least, for if you're missing class on Thursday, going through the trends for ionization energy and electronegativity, and then also talking a little bit about the discrepancies. Okay, so you already have the graphs for ionization energy and the data on the PowerPoint here. This is the graph for ionization energy also that you should contain as a reminder of what ionization energy is. Ionization energy is a measure of the amount of energy you need to remove a valence electron. Okay, so how much energy it takes to remove one valence electron. If you just look at this graph and look at the trends, okay, if you look at lithium to neon, that's your row 2. So period 2, lithium to neon, we can look here and say, what's the trend? Well, the trend is as I increase my atomic number moving across a period, the ionization energy increases. So what about going down a group? Well, if you look at a group, say for example, the alkali metals, they're at the bottom of all of these lines. As you go from lithium to sodium to potassium to rubidium, you'll notice you're progressively going down. So the trend for ionization energy then is as I go down a group, my ionization energy decreases. So let's talk about why. And this is actually in your notes. Okay. Oh, sorry, this is the trend. So it increases across a period and it decreases down a group. So why is the trend the way it is? Let's go first for across. Why, when you go across a period, does your ionization energy increase? Well, think about what ionization energy is. Ionization energy is the energy it takes to remove an electron. As you go across a period and you add more protons and you add more electrons, those electrons are being drawn closer and closer to the nucleus. They're feeling a bigger and bigger nuclear charge, so it's just going to take more energy to pull them away from that nuclear charge. Okay. So as you go across a period, it gets harder and harder because the nuclear charge is so big, it's hard to take that negative charge away. Instead, these elements, as you move across like that, have more of a tendency to draw electrons toward it rather than let one leave. And you can even just think about this as simply as, alkali metals, they want to give up one electron. How much energy is it going to take to remove that one? Not a lot. Fluorine doesn't want to give up one. How much energy is it going to take to remove one? A whole bunch. So ionization energy increases across. Ionization energy decreases going down though. Why? Well, it's basically the same explanation I used as when I talked about why your reactivity of alkali metals increases as you go down. Okay? As you add more electrons and you fill your shells, you have less nuclear charge pulling the electrons. Okay? You're further away from the nucleus, you have less charge, and the electron shielding is shielding that charge from getting to your valence electrons. So that explains the trends both across a period and down a group. Let's talk about the discrepancies. So if you look at the graph, let's say for example in period 2, so again from lithium to neon, you'll see that generally your ionization energy increases, except in 2 little spots. In 2 little spots, instead of it just increasing, it dips down a little. Okay? Instead of moving, as you move across the period, instead of the ionization energy increasing for every one that you hit, some of these dip down. Why? Well, if you look at your graphs and you actually determine what elements correspond to these 2 little dips, what you'll see is this first dip happens. What you're going to see is this first dip happens between beryllium and boron. Beryllium's at the top and then boron's down a little bit. The trend is that boron should have a higher ionization energy than beryllium does, but in practicality, that's not true. Okay. Why not? Well, let's think about what the difference is between beryllium and boron. What happens for beryllium is you have your complete sublevel s full. And then for beryllium, you're putting your first electron in the p orbital. What we find is there's this little measure of stability when you complete a sublevel that allows for the trend to adjust itself slightly. So it is harder to remove the one electron from the complete s orbital for beryllium than it is to remove that one p orbital. Okay. So let's look at how this trend continues. The other little discrepancy that happens right in the middle of the trend is between nitrogen and oxygen. So nitrogen is at the top of that peak and oxygen is down, meaning the trend should say that the ionization energy for oxygen is bigger than nitrogen, but we find it's less. What does that mean, that the ionization energy for oxygen is less? What that means is it is easier to remove an electron from oxygen than it is from nitrogen. Why? Well, nitrogen has 3 electrons in the p orbital, meaning it has 3 electrons, 1 in each orbital orientation of p. It has 3 electrons all spinning the same way, and we find that this is more stable than if you were to have like one set of electrons paired and the other 2 not paired. So it is harder to remove one of the unpaired electrons from sodium than it is to remove one electron from oxygen. Okay. So 2 places this discrepancy is occurring: at the end of an orbital or halfway through an orbital. So oftentimes then people ask me, okay, so let's look at the row 3 and see that this is still consistent here. Okay, going from magnesium to aluminum, you can see that aluminum doesn't continue to increase its ionization energy, it goes way down. And then that middle peak, the discrepancy, is between phosphorus and sulfur. So it still happens here, that the discrepancy, meaning the trend is not consistent, at the end of the S block and halfway through the P block. So as you start to learn this, everyone always asks me then, well, doesn't this happen at the end of the P's too? And I'm like, dude, look at the graph. Okay, your peaks on here are at the end of your P. Yeah, it happens in the P, right? You have a huge drop. After neon, you have a huge drop down. It's way easier to take them from the next energy level up than from the P. Okay, so at the end, once you've filled a sublevel and once you've half filled a sublevel, you tend to have a degree of stability where it's harder to remove an electron than it should be. If you take a look at even group 4 here, my graph is not great on here, but you could see on your graph, and it's not bad here, you can see the discrepancy at the end of the D block. Okay, so the end of the D block, again, it's harder to remove one from zinc than it is from gallium because zinc has a full sublevel and it's hard to take one of those electrons away. And that trend continues. So those are your discrepancies. You need to be able to state the location of the discrepancies and the why of the discrepancies. This might not make a lot of sense, but we can go through it again on Friday. The one other thing about ionization energy is there's more than just one ionization energy. The graph you guys had was actually for the first ionization energy. First ionization energy is how much energy does it take to remove the first electron from any atom. There is second ionization energy, third ionization energy, fourth ionization energy, and so on. What that means is the second ionization energy will be how much energy does it take to remove your second electron. And your third ionization energy will be how much energy does it take to remove your third electron. And here I'm not asking for you to understand the trend, but I am asking you to understand the effect, okay, how the electron configuration affects the magnitude of the different ionization energy levels. So right here is just a graph of that period 2, right? The red line is the line we've been working with all along, our first ionization energy. So the trend is as you move across your period, the ionization energy increases. It gets harder to remove an electron because of the full pull of the nuclear charge. Now, if you look at your second ionization energy, which is the blue line on this graph, what you'll notice here is lithium has a gigantic second ionization energy, and then it drops significantly down to beryllium. Why? Well, this is the energy that it takes to remove a second electron from an atom. Does lithium want to let a second electron go? Right? All lithium wants to do is lose one electron. So it has a very low first ionization energy. But if you try to take a second one away, it requires a massive amount of energy. It requires as much energy to take that away as it does to take away an electron from neon. Okay, that's insane. Now, if you notice and just compare beryllium, its first ionization to its second ionization, you can see how low beryllium's second ionization energy is. That's because it's already lost one, right? And it's very happy to lose both then to get rid of that s orbital. And all of them here, if you look at them, have a lower second ionization energy. It's a little bit easier to take their second electron once you've already gotten rid of one. Okay, that's just kind of life. So the graph on the right also shows you that this is a consistent trend. Okay, it's harder to take your second electron away from lithium, just like it's harder to take it away from sodium, just like it's harder to take it away from potassium. Okay, that first column will always have a higher second ionization energy. Let's talk about the third ionization energy. If we saw this graph of the third ionization energy, what would you expect it to look like? You could expect that lithium would still have a very high third ionization energy because it doesn't want to lose 3. Beryllium now should have a significantly higher ionization energy because it doesn't want to lose 3. But borons would still be pretty low because it's more than happy to lose a third electron. And you can just continue this trend. If we talk about a fourth ionization energy, you can assume that lithium, beryllium, and boron would all have very high third ionization energies, where carbon would still have a relatively low third ionization energy because it can potentially give up 3 electrons. And you can just keep doing this. I mean, you can go all the way to like past 4, it gets a little dicey in terms of the ability and how much energy it takes to actually remove more than 4, but you can keep doing this, okay, in terms of where your peak would be and where your valley would be. What you need to be able to do with this is identify, depending on which ionization level you're talking about, what elements would have a very high energy for that ionization and which ones would have a very low ionization for that energy. So for example, if we're talking about the second ionization energy, all your alkali metals would have a very high second ionization energy because it takes a lot of energy to remove them. Basically anything that would take a 1+ charge, it would take a lot of energy to take away a second one. But anything with a 2+ or bigger would have a low second ionization energy. So if you're working with like the fourth ionization energy, anything that usually takes on +1, +2, or +3 would have a very high fourth ionization energy. But anything that could take on a +4 or potentially bigger would have a low fourth ionization energy. The other trend that we're talking about on Thursday is electronegativity. And electronegativity is a measure of the tendency of an atom to attract electrons to itself. Okay, when we get into bonding, there's going to be 2 types of bonding: the ability to remove electrons, and that would be based on ionization energy, and the ability just to attract electrons to itself, which is electronegativity. You can see the trend here. This trend looks very similar to ionization energy, Less discrepancies, which is fine, but it looks very similar. So just like ionization energy, the first line on this graph is your period 2. It goes from lithium to not neon this time because we don't have any information on the noble gases for this one because they don't really bond. And it's all about figuring out how it pulls electrons toward itself in a bond. So in this case, it just goes to fluorine, and you can see the least electronegative element here in that period is lithium, and the highest is fluorine. So the trend is the exact same for electronegativity as it is for ionization energy. As you increase your atomic number across a period, you increase your electronegativity. And if you look at all your alkali metals or all your halogens are all your peaks and your alkali metals are all of your lowest points, you can see that the trend, as you increase your atomic number down a group, your electronegativity decreases. But again, if we talk about why this is happening, the explanation for why electronegativity is the way it is the exact same as why ionization energy is the way it is. It's just looking at the reverse aspect. For electronegativity, we want to draw electrons toward ourselves, and the greater numbers are a better tendency to draw the electron toward yourself. So across a period, the reason why the electronegativity gets so much bigger is it's basically your nuclear charge, again, increases, and the atomic radius is pretty small. So it's easier to draw electrons toward yourself because the nuclear charge is so big. Down a group, you're increasing your energy level and you're increasing your electron shielding. So you have less nuclear charge that's going to be pulling electrons from an adjacent atom. So again, going across a period, the reason why you have increasing electronegativity is increasing nuclear charge. And as you go down a group, the reason why you have decreasing electronegativity is you have an increase in shielding. Okay. So let's look at electronegativity quickly and talk about discrepancies. Electronegativity doesn't have as clear of discrepancies as ionization energy does. If you look at our first part of this graph where you have D elements that have their electrons in D, and you counted these, you'll notice that there is a slight downward at the fifth D element and a slight downward at the first P. So if you remember with ionization energy, I said halfway through an orbital, there was this island of stability where there's less of an ability to take away an electron, which means more of a tendency to draw electrons. And that's what's happening in the D block. Halfway through the D block, you have this valley where it's harder to take them away and easier to draw them toward yourself when it's half full. And the same thing happens once you've got, basically, once you're completing or filling your D block. Okay. So there's these half full and complete fulls where we have a degree of stability, a degree where they don't want to lose electrons. They pull a little bit closer and they're going to draw electrons toward themselves a little bit better. Okay. So there are still discrepancies in electronegativity. Focus on the discrepancies in ionization energy because they're more clean and clear. But basically we see repeated here that halfway down a period and all the way at the end. But basically we see here again that halfway through an orbital being filled and then all the way through an orbital being filled, we have a tendency for things to be a little bit different than what you expect. Okay. This might not do it for you. With this, I want you to do the second page of that graphing activity. It's explaining all the whys, articulating all the whys. When you come into class on Friday, we'll do reviewing, we'll walk through this again. If you want to come in Friday before school or after school, that might be a really good idea to walk through this verbally with me. And then don't forget to be prepared for your periodic table test. Okay, see you guys Friday.